All right, there's 2-3, day 2. Still kind of staying in the focus of 2-3 of reading graphs. Specifically, though, we want to look at identifying intervals where a graph is constant, increasing, or decreasing. Okay, it tends to be a big thing in calculus is identifying, not just graphically, but in calculus, you get into the algebra of how to do it without a graph, as to where a graph is increasing, decreasing, or where is it just staying the same, which we would call constant. We are just going to take a look at how we do it from a graph. You would always describe the intervals from left to right. Okay? And in particular, I'm going to describe it in x values. So I'm looking down here, okay? I'm not going to cite any of the y values because it just doesn't work that way. When we're saying here's the x values for where this graph is in the first problem, decreasing. Okay, I can see that is from, looks like here to here. Okay, so in the graph here, it looks like -2 to 0. And we typically state them as open intervals. Okay, between -2 and 0. Okay, that graph is decreasing. I continue from here to here, right? The graph is neither increasing nor decreasing. It's what we would call constant. I describe it just the same way. It's a constant graph from 0 to 2. Again, in terms of the x values. And then here to here, right, which looks like 2 to 4, we would call that graph increasing. Okay? Left to right, looking at the x-axis. Okay? Is how we go about stating where it's increasing, decreasing, or constant. Let's look at a few more. Okay. First up, we'll go increasing. Where is that graph increasing? Okay. Now there's no, dots to end it, so I'm going to assume here that we've got some arrows going this way. Okay. Increasing, it looks like two different spots. We didn't see this on the first example, but it could happen that it has two separate intervals where it's increasing. Okay? It looks as though basically from here on, going in that direction, it's increasing. So that tail goes down and it never comes up. So over to the left, I would say -infinity up to -1, right? I noticed, the point -1, 2, it hits a little maximum, and then my graph changes direction. Okay, so that's where it stops. Now in a minute here, I'll mark decreasing. We'll get to that. Because that's what's going on. As I'm looking at it left to right, I see, okay, there's a middle part there where the graph turns and starts to decrease, but then at 1, right, which would be right here, it goes back to increasing. Okay, and 1 up to infinity. As you see that arrow, that after it gets past 1, that graph starts to increase and it never comes back. Okay, it's increasing for any x value that you put in bigger than 1. Decreasing, it looked like there was just the one interval right here in between. So there it looks like from -1 to 1. That's the only interval where you've got a decreasing graph. Now, the third piece that we looked at on the slide before was where is the graph constant, okay? Now, here it kind of looks like nowhere, right? The three intervals that we cited take care of all the possibilities. You've got two where it's increasing and one where it's decreasing, and we just leave it at that. So technically, you may find, and this would be true of a lot of functions that we work with, the constant piece might be happening at a point, not necessarily an interval, but it is precisely at the points -1 and 1 where we say the graph is constant, at that maximum and minimum, just at that point. Notice I didn't cite an interval, okay? But at those 2 points, the graph is neither increasing nor decreasing. As soon as you go past, whether it's above or below either one of those points, the graph is once again increasing or decreasing, okay? Not everyone would be like that it has this, the looking ahead to the next one. You can see a little interval there in the middle where it's constant, okay? And the first one had that as well. This one doesn't have that. It has kind of these rounded peaks where it hits a max and a min. Increasing looks like one interval over to the left. I'm assuming that continues. Negative infinity, and then it goes up to 0, right? Which would be right here. At that point, it appears as though that graph changes from increasing to a constant. Now we'll get to the constant last. Let's go look where it's decreasing. After it's done being a little constant graph, it changes right here and starts to go down. So it looks like anything past 2, we'd call that graph decreasing. Anything past 2. Let's go take a look at the constant. Right in between, perfect horizontal line, right? When we say constant, it means the y value doesn't change, right? That's right at y equals 1. And between those two x values, it doesn't change. Doesn't go up, doesn't go down. So I would say between 0 and 2, you have a constant graph, okay? So that one's more like the one from the slide before, where you do have an interval where it's constant, okay? Again, that first one we did on this slide is a little bit different, right? It was just kind of these smooth, rounded curves and kind of slowly changing directions, where there was a couple points where it was constant, but no intervals. All right, let's go to the final one here. Kind of an interesting one. Increasing, right? Well, so I'm looking left to right. Is that graph going up and down? And it's going up, right? It looks like right here there's a change, but that change appears to just be the slope, right? Once I get past that point, the graph is still increasing. It's just not increasing as fast. But when we're identifying these intervals, we're not getting into how fast or slow is it increasing or decreasing. That's not the question. Is it increasing? Right? It still is. And then we get to right here, and the graph picks up again, and it starts to increase faster, and the line has a steeper slope. Doesn't change the fact that it's still increasing, okay? The graph is increasing everywhere. I look through it, I don't see on the other two pieces that we would look for, if I were to go decreasing, nowhere. You couldn't find an x value where that graph is decreasing, and the same is true for constant. Nowhere, right? That graph is increasing everywhere. Okay, and that's not a really uncommon characteristic of a graph, right? Obviously, we've known and I've seen many times before, that's true for lines. Now, that's kind of a funny graph. I mean, if we were to look at its equation, it would probably be a piecewise graph, right? Because it looks like you have a line, right? And then it changes to a different line, and then it changes to another line, okay? The thing is with those three lines, even if they were characterized by different equations, they all have positive slopes and they're all increasing. So nowhere is it decreasing, nowhere is it constant, okay? We'll see some other graphs throughout the year, right? The first one that's coming to mind is an exponential, which we haven't seen. That one also has that characteristic. It's a very different graph from a line, but it also has the characteristic that it doesn't change direction. It's either always an increasing graph or always decreasing. So that one might feel kind of weird that the graph didn't change directions, but some graphs do that because some functions model data that doesn't change directions. That's okay. That happens. All right, we'll call it quits there. 2-4. We will kind of broaden up our discussion of function families and different kinds. Okay, we're going to do a little bit more. So far, again, we've talked about lines and quadratics and really gone deep. In 2.4, we're not going to have anywhere close to the depth that we've covered with lines and quadratics, but it's time to branch out a little bit and see that there's other functions out there besides those two, and now's a good time to see them.